In this video, we're going to learn about Bohr calculations. So, if we look at the Bohr model of the atom, the electrons are pulled in towards the nucleus. And what we can say is that a free electron that has no association with a nucleus, we're going to say that its potential energy is zero. But as it gets closer to the nucleus, the potential energy is going to drop into the negatives. If we're talking about the hydrogen atom, the energy of the electron, or the potential energy of the electron, is calculable through a relatively simple equation, which is right up here. So what this says is that at energy level n, the energy is equal to, or the potential energy is equal to negative Rydberg's constant times 1 over n squared. Rydberg's constant is listed right here, 2.18 times 10 to the negative 18th joules. And what we see is that if the energy level is 1, then negative Rydberg's constant times 1 over 1 squared is just negative Rydberg's constant, which brings us down here at negative 2.18 times 10 to the 18th, negative 18th joules. If the electron raises to the n equals 2 level, well, then our 1 over n squared changes from 1 over 1 to 1 over 2 squared is 4. And so we are at a smaller fraction. We're actually at a quarter of Rydberg's constant. And so we only have negative 5.45 times 10 to the negative 19th joules. And you can see as n grows, we get closer and closer to 0. So that tells you the potential energy of the electron at a given level. But as you're probably aware, in the Bohr model, electrons can undergo transitions. They can transition from the n equals 1 state up to the n equals 5 state, and that requires absorbance of energy. A photon has to strike the electron in the first shell and with exactly the right energy to bring it up to the n equals 5 shell, or the n equals 4 or 6 or 2 or whatever. As long as the photon of light has exactly the energy required to make the transition to occur, then it will occur. But we need to understand the relationship between these energy transitions and the energy of the light and the photon wavelength required to make it happen. So here is our equation again. And what we're going to do is we're going to use the simple principle that a change in energy is equal to the final energy minus the initial energy. So if we want to find out the photon energy for something a photon that is released when an electron drops from a high energy level to a low energy level, this is what we use. Or if we want to figure out what is the photon energy required to cause an electron to go from one state up to a higher state, this is what we'll use. If we take this equation right here and we substitute in what we know for energy, we can say that the change in energy is equal to, it's going to be negative R sub h times 1 over n final squared minus, we're going to have negative R sub h times 1 over n initial squared. And I guess I could put this in parentheses if I want as well. So right here, this is just our EF. I'll put more parentheses around. This is our EF, and this is our EI over here. EI and EF. And if we play with this, we could factor out Rydberg's constant, and to get rid of the negative, we could flip them. So we end up getting here, which is delta E equals Rydberg's constant, positive Rydberg's constant, times 1 over n initial squared minus 1 over n final squared. If we wanted to keep the negative Rydberg's constant, we would just have to make it final minus initial. And let's try a problem now where we're applying this formula. So an electron in the hydrogen atom falls from the n equals 3 state to the n equals 2 energy level. Determine the energy and the wavelength of the photon associated with this transition, and is energy absorbed or emitted? First of all, I'm going to answer this question, this last part, because I know that the hydrogen atom's electron is going down from the third level to the second. And if that's happening, it's dropping, it's releasing energy. So we can say that energy is emitted. And so what's going to happen is, as the electron falls, a photon will be released with a certain energy and a certain wavelength. What values those are, we're going to have to figure out right now. So I know that delta E is equal to the energy final minus the energy initial, and I can use my equation. Delta E is equal to Rydberg's constant times 1 over n initial squared minus 1 over n final squared, and that is equal to 2.18 times 10 to the negative 18th joules times, okay, I've got 1 over, my initial is n equals 3, so 1 over 3 squared, minus the final is 1 over 2 squared. So there we go. And what this comes out to is negative 3.03 times 10 to the negative 19th joules. And that is delta E for n equals 3 going down to n equals 2. So that gives me the energy, and because this is a negative value, we know that energy is emitted. If we had gone in the opposite direction and we'd had 1 over 2 squared minus 1 over 3 squared, this would be a positive value, and we get a positive delta E, which means energy would have to be absorbed to make that happen. That would be the reverse. Now, from here, if we have the energy, we know that energy equals hc over lambda. And in this case, we know that energy is negative 3.03 times 10 to the negative 19th joules. And that is equal to Planck's constant, which is 6.626 times 10 to the negative 34th joules seconds. And we're multiplying by 3.00 times 10 to the 8th meters per second over lambda, which is unknown. Our seconds and our inverse seconds cancel out, and what we will find is also, if we rearrange things, we get lambda times this many joules is equal to this many joules times meters. So what we would have to do is go lambda is equal to essentially Planck's constant divided by the energy that we have here, and the units will work out. We get 6.56 times 10 to the negative 7th meters. And if we wanted to do a conversion, I suppose I didn't ask for nanometers, but if we needed to, I could multiply this by 10 to the 9th nanometers for every 1 meter, and I would get 656 nanometers if I needed. And this should make sense, because if you do look at the Balmer series, you will find that the n equals 3 down to the n equals 2 level, that associates with a wavelength of 656 nanometers. It's in the red part of the visible spectrum. So finally, I've got one more problem that's challenging in the sense that, well, mathematically, there's a bit going on here. So an electron in a hydrogen atom falls from an excited state to the ground state, releasing a photon with wavelength of 95.0 nanometers. What was the electron's energy level initially? Well, I know that my lambda is equal to 95.0 nanometers. I know that the final state, the final n, is the ground state, which means 1. But my n initial is unknown. So I'm going to need to use my Bohr equation. I need to know delta E equals energy final minus energy initial. I need to use that, but I don't have those energy values. And I don't have the value of delta E. I don't have that because I only have the wavelength of the photon that's released. So I'm actually going to need to figure out the energy of the photon, which is equal to hc over lambda, which is equal to 6.626 times 10 to the negative 34th joules seconds times 3.00 times 10 to the 8th, that's 8 here, meters per second. And I'm dividing by my wavelength, which is 95 nanometers. There's a problem here because I've got nanometers and my speed of light is in meters per second. So over here, I'm just going to quickly figure this out. I've got 95.0 nanometers times 1 meter over 10 to the 9th nanometers. And that's going to be equal to 9.5 times 10 to the negative 8th meters. And so now I can say this is divided by 9.5 times 10 to the negative 8th meters. So my energy of the photon that's released is equal to this quotient, which is going to come out to 2.09 times 10 to the negative 18th joules. So there we go. That is the energy of the photon that is released. Now, if I know that my delta E is equal to 2.09 times 10 to the negative 18th joules, and actually, hold on, this is a photon that is released, so I need to make this a negative value because the photon is released. So that is going to be equal to Rydberg's constant times 1 over n initial squared minus 1 over n final squared, which is now going to give me, all right, negative 2.09 times 10 to the negative 18th joules is equal to Rydberg's constant, which is 2.18 times 10 to the negative, this is going to be 10 to the negative, what is it, always 18th joules, times 1 over, now I need my n initial squared, and that's going to be unknown, so I can say 1 over ni squared, minus 1 over n final squared, which is just 1 squared. And what this comes out to next is negative 2.09 times 10 to the negative 18th joules is equal to 2.18 times 10 to the negative 18th joules over n initial squared minus, well, this is just going to be 2.18 times 10 to the negative 18th joules, because I'm multiplying that times 1 over 1 squared. And if I add the 2.18 times 10 to the negative 18th joules to both sides, I find that we get 9 times 10 to the negative 20th joules is equal to 2.18 times 10 to the negative 18th joules over Ni squared. If I multiply both sides by Ni squared and I divide both sides by 9 times 10 to the negative 20th joules, then what I will get, and then I have to take the square root of both sides, what I will ultimately get is that Ni is equal to 4.92, which is, at first consideration, this is a problem because there is no n equals 4.92 state. But in truth, there's some rounding that I did here, and really it's 5. So Ni is equal to 5. Whenever you get a number, I think a good rule of thumb here is if you end up getting to the n squared and you find that you've got pretty much a perfect square, like in this case, it would have been pretty close to 25 is equal to Ni squared. Well, if you get there, you know you're good. Take the square root and just say that whatever you come out to, round it to the nearest one. As long as you're within a pretty close margin you're of a whole number, you're going to be fine, and it means that you've done it right. So always you want to look for perfect squares, and then you take the square root and get to a whole number or something very close to it. If you are quite far off, then it means that you did something wrong, and you should really be careful. I also want to point out that sometimes you can tell based on the wavelength, you can tell a little bit about what you're trying to find. So for example, if let's say we were given that we started in the n equals 5 state and we dropped down to an unknown energy level, well, if we know that we're starting in the n equals 5 state and the wavelength is 95 nanometers, 95 nanometers is easily into the ultraviolet, and we know that the Lyman series, which ends in n equals 1, that is in the ultraviolet range. Similarly, if you had something in the visible spectrum, you would know that you're probably dropping down to the n equals 2 state. And if you were in the IR range, which can be a bit tricky because it goes up quite a ways, but oftentimes that would mean that the energy gap ends in n equals 3. So just something to keep in mind. It's a good way to check your work. So I hope this video has been helpful. Let me know if you have any questions or comments in the comment section below. Thanks.